Let's go back to cellular respiration now and add in some more information from what you learned before. So you'll recall that you have a cell, and your cell has a mitochondria, and you have your blood, and we take glucose and oxygen from your blood. They go into your cell. You do the whole glycolysis, acetyl-CoA, Krebs cycle, electron transport. You get your ATP. You get heat, and you end up with 6 carbon dioxide and 6 water going back into the blood. So what we're going to focus on in this lesson is that carbon dioxide that goes back into the blood. So every time you do cellular respiration, you put 6 carbon dioxides into the blood. We're going to follow this carbon dioxide and see what happens with it. Blood, as you may know, is mostly water. So we have carbon dioxide being mixed in with H2O. They react with each other. There's a chemical reaction you get when you put carbon dioxide in water. You already know this because of your Chapter 1 lab. You used your straw to blow into the bromethyl blue and you turned it from blue to yellow because the carbon dioxide you were blowing out was having a chemical reaction with the water in the beaker. These two molecules will combine with each other. H2CO3. All that is carbon dioxide and water together. So H2 comes from right here, C from the C, and you have 2 oxygens and carbon dioxide, 1 oxygen and water. That gives you O3. H2CO3 is carbonic acid. Now it doesn't stay like this. It dissociates. Remember, you've already learned about the word dissociate. We talked about like when salt mixes with water, it dissociates into sodium and chloride ions. Carbonic acid in your blood dissociates. One of the hydrogens breaks off. So one hydrogen leaves. Now remember before when we talked about hydrogens breaking off from water, hydrogen has 1 electron. When it breaks off from a molecule, it leaves its electron behind. So the HCO3 keeps that electron. So it has a negative charge because it kept the electron, and electrons are negative things. The H by itself has a positive charge. It no longer has an electron. It left its electron with the molecule. So it's out here without an electron. Electrons are negative. It has none of them, so it is positive. This one, HCO3 minus, is bicarbonate. It's often called bicarb for short. And this is hydrogen ion. Think back to what you learned about pH. An acid is anything that increases the concentration of hydrogen ions. So because we're adding a hydrogen ion, this lowers the pH. This hydrogen ion results in reduced pH. So the effect is every time your cells do cellular respiration, they lower the pH of your blood. So your cells make ATP. When they make ATP, they put carbon dioxide in your blood. This reacts with the water in the blood, and you end up increasing the number of hydrogens in the blood. And when you increase the number of hydrogens, you reduce the pH. So this is tying in with what you did in the Chapter 1 lab. You first experienced this in Chapter 1 lab. Now we're just kind of formalizing it and giving you notes to go with that. Your blood has to stay at a pH of 7.4. Think about why it's dangerous to change that. You should know by now. If you change pH, you denature proteins. Enzymes are proteins. And remember, you rely on your enzymes to stay alive. It's so important to keep your blood at 7.4 so you don't denature your enzymes. On one side, you have cells. Your cells are making ATP, and in the process of making ATP, they put carbon dioxide into your blood. Every time you put carbon dioxide into your blood, you get more hydrogens and your pH drops. Well, if you just let this go, your pH would drop, you would denature your enzymes, and you would die. So that's not a good option. Luckily, we have your lungs. Your lungs take the carbon dioxide out of your blood and exhale it. You have to maintain a balance. You want to keep homeostasis. Think about what would happen to pH if you took too much carbon dioxide out of the blood. If you were taking too much out, your pH would go up. So if you have too much CO2 in your blood, you have a low pH. That can kill you. However, if you have not enough carbon dioxide in your blood, you would have a high pH, which also could kill you. So you have to maintain just the right amount of carbon dioxide. So the amount that goes in has to equal the amount that goes out. So let's say, we should make up some numbers to make it easy. Let's say you have 100 carbon dioxides in. That means you need 100 out. Let's say then your cells start using a lot more energy and you have 500 carbon dioxides in. Well, that means you need to get 500 out. And in order to increase, to get 500 out, 400 more than you were before, is where you have to breathe deeper. And your blood is what's transporting this from your cells to your lungs, and your heart is what pumps your blood, so you need your heart to beat faster. Which is exactly what you saw in your Chapter 1 lab. So cellular respiration plays a big role in your pH. And your breathing rate, the reason you breathe heavy when you exercise is to get rid of that extra carbon dioxide so you can keep your pH at 7.4. A lot of people want to say, oh, you breathe heavy so you can get more oxygen. You do use more oxygen when you exercise, but that's not why you breathe heavy. You breathe heavy to get rid of the extra carbon dioxide and keep your pH at 7.4. Let's look at another aspect of cellular respiration now. When you are exercising full force, as much as you can, so when you are full out exercising, say you're running a marathon, right? You're giving it your all. You do use a lot of oxygen. Remember, for each time you do cellular respiration, you use 6 oxygens. So you do use a lot more oxygen. Your heart and your lungs do send more oxygen when you're exercising. Yes, you are breathing deeper and faster. Your heart is pumping faster, so you are sending more oxygen. But if you look at your muscles on one side, when you're exercising, your muscles use oxygen. So they are taking it out of your blood. And on the other side, you have your lungs and your heart are putting oxygen in. When you exercise as hard as you can, it's not equal. You don't have an in equals out situation. Instead, what happens is your muscles use more. There is more going out than what is going in. So the result of that is the amount of oxygen in your blood drops. So in this scenario, exercising as fast as you can, your muscles use more oxygen than your heart and lungs provide. The result of this is a decrease in your blood oxygen level. And you go into a state of oxygen debt. Once you're in oxygen debt, you can no longer supply oxygen to every cell. You have to start rationing. So let's look at what happens to a cell if it doesn't get oxygen. So remember, we have the cell, we have the mitochondria, you have your blood, and we'll put the glucose here. But we're not going to put any oxygen there to go into the cell, just the glucose. So if the cell has just the glucose and not the oxygen, it can still do glycolysis. Remember, glycolysis occurs in the cytosol next to the mitochondria. So we're going to take that glucose and we're going to pull out 2 hydrogens. We're going to have our 2 carriers come along to pick them up. Then we're going to take what remains, break it in half, so we get our 2 pyruvates. And we have a net gain of 2 ATP when we do this. Glycolysis can still happen just fine. Normally, those pyruvates would go into the mitochondria. But when there's no oxygen, they can't do that. Mitochondria shuts down. And the pyruvates can't get in. This reminds me of the National Lampoon's movie. So you might be wondering what these pictures have to do with anything. If you remember the National Lampoon's movie, they drive across the country to get to Wally World. So here are the Griswolds. They're the pyruvates. They're ready to get into Wally World, just like the pyruvates are ready to go into the mitochondria. And if we skip up a little bit,
Sorry, folks, we're closed for 2 weeks to clean and repair America's favorite family fun park. Sorry. What?
Clark, what are you doing?
We watch his program.
so you get the point. The Griswolds are the pyruvates. This is the Griswold family. The mitochondria is Wally World. The Griswolds want to go into Wally World, but they can't because it's closed. The pyruvate wants to go in the mitochondria, but without oxygen, it's shut down. So, if you've seen the movie, the Griswolds are trying to get into Wally World, and a security guard, John Candy, comes out and says, "Sorry, folks, park's closed. Moose out front should have told you." So I always imagine a little moose standing here. So draw in a little moose here in front of the pyruvate. And the moose or in front of the mitochondria. And the moose says, "Sorry, pyruvates, mitochondria is closed." So now what do? Your pyruvates can't go into the mitochondria. No electron transport. You're not going to get those other 34 ATP. You're just stuck here. And you have your NADH. Remember, this is a taxi cab. Imagine you're in a taxi cab and you fly somewhere, you get to the airport, you have the taxi cab take you to a concert you're going to. Well, you get there and it turns out the concert is canceled. What are you going to do? You can't just stay in the taxi cab. You have to get out of that taxi cab. You have to find someplace else to go. Same thing here. The NADH is not going to keep the H. It's got to get rid of it. So you're going to put the H back onto the pyruvates. So now you get C3H6O3. This is lactic acid. So if you lack oxygen, you switch from cellular respiration to fermentation. In fermentation, you can only do glycolysis. You're not going to use your mitochondria. You're only going to get 2 ATP. Now remember before you got 36 because there were another 34 that came from electron transport. You're not doing that now. So your payment has gone way down. Remember I said this is like a cell's job. Imagine you have a job that pays $36 an hour. Then one day you go into work and your boss is like, "Yeah, today I'm only going to pay you $2 an hour." That's not so good. Also, instead of the pyruvates going in and finishing being broken down, they get the hydrogen added to them and you get lactic acid. Now, lactic acid is going to reduce the pH in your muscles. Enzymes don't just instantly denature, they slow down first. So this slow drop in pH is going to inhibit your enzymes. They're not going to work as well. So you're only getting 2 ATP, the pH in your muscles is dropping, which is making it hard for your enzymes to work, and you are going to stop exercising. So imagine I said hey, I'm going to give extra credit to anybody who can hop up right now and run all the way to Peoria. And you have to sprint as fast as you can the whole way there. You can't stop, you can't take a break. You might give it a try, but chances are I'm going to have to come along and find you in the ditch on the side of the road. Unless you're an amazing super athlete, you're not going to make it because your muscles are going to use oxygen faster than your heart and lungs can send it. Your cells are going to switch to fermentation. They're only going to get 2 ATP. There's going to be lactic acid building up, and you're going to stop. One interesting thing to think about is athletes, when you train, if you wanted to run to Peoria, it is humanly possible. You would have to train a lot. Think about what gets better when you train. Even if you didn't want to run all the way to Peoria. Say you just want to run a 5K. If you train, you'll eventually be able to do it. It's your heart and lungs that get better. Athletes can keep running for a longer time than somebody's out of shape. Yes, their muscles are better, but it's not just the muscles. Their heart and lungs are better at sending oxygen, so they don't switch over to fermentation as quickly. Their heart and lungs are able to keep up with the muscles' demand of oxygen. So their cells don't switch to fermentation. And you can tell this if you know anything about heart rate, if you know about athletes' heart rates. An average adult resting heart rate is 75 beats per minute. An athlete's resting heart rate can be in the 40s, can be 40 to 50 beats per minute. That's an indication that their heart is really strong and really healthy and working good, because their heart is so efficient that it doesn't have to beat as much when they're at rest. So an average adult at rest, just to keep up with keeping the body alive, has to beat 75 times a minute. An athlete's heart is so good at sending oxygenated blood that when the athlete is rest, their heart only has to beat 40 times a minute to keep the body going.